Today we are going to look at the free response questions for the 2014 AP Calculus AB exam. Keep in mind there are 7 common free response questions that the AP exam likes to do. We'll take a look at the end and see how many of these 2014 had. For the first two, we're allowed access to a graphing calculator. Grass clippings are placed in a bin where they decompose for 30 days. The amount of grass clippings remain in the bin is modeled by A of t. As soon as I see some equation like this, I'm typing it in as y1 on my graphing calculator, where A of t is measured in pounds and t is measured in days. Find the average rate of change of A of t over these 30 days. Indicate units of measure. This is your average rate of change formula. If you want to type in something like y1 of 30 and it's stored as y1, you can just type this in one line in your calculator. You should get negative 0.197 pounds per day, and that's awarding 1 point. Find the value of A prime of 15. Using correct units, interpret the meaning of the value in context of the problem. This is the derivative of A at 15. With access to a graphing calculator, I can hit Math 8 to do the first derivative of my function, and I can input 15 as the value, and I get negative 0.164. Because the derivative is negative, I can say that the amount of grass clippings in the bin is decreasing at a rate of 0.164 pounds per day at this time. Finding the derivative is 1 point, and your interpretation stating that it decreases at this time is another. For C, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over 30 minutes. So I want to find the average amount of grass clippings in the bin. The average amount of something, I'm going to do 1 over b minus a, the integral of what I'm taking the average of. So this is the amount of grass at different times. I'm going to find the area under the curve and divide it by 30 in a way. You get 2.753. I want to know when the amount of grass in the bin is at this value. And so what you can do is graph these. I have A of t graphed as my y1, y equals 2.753 as my y2. Second, Calc 5 can give you the intersection of any two lines, and it tells you the time that this happens. Just by writing out an integral with 1 over b minus a for your average is 1 point, and providing the time of 12.413 is another point. For t greater than 30, L of t, the linear approximation to A at t equals 30, is a better model for the amount of grass clippings remaining in the bin. Use this line to predict the time at which there will be half a pound of grass clippings remaining in the bin. So we have something modeling it for 30 days. I want to know what happens a bit later, really how many days into decomposing grass will it take to reach 0.5 pounds of grass remaining. So we need to create a linear approximation line. I am a big fan of point slope form, where m is going to be the slope at 30, because that's the last bit of information I know. And then I'm going to have a linear a line after that. Help me approximate what's going to happen past 30. So the slope at 30, my calculator with Math 8 can just give me negative 0.056. The only other thing I need for point slope form is a coordinate, and the last coordinate that A of t model gives me is that at 30, there's about 0.785 pounds of grass remaining. So I can plug in my x value and my y value and my slope. And if you solve for y, you can write this as L of t if you'd like. You have an equation that can be used to predict what happens after that 30th day. I want the amount of grass to be 0.5. And with a bit of algebra, you can solve for x to be about 35 days after this decomposing process. 2 points for your expression L of t. 1 point for setting L of t equal to 0.5. I did that here or there. And then 1 point for your answer. Keep in mind, every free response question is worth up to 9 points. Your goal is for half or more on each. And I think all of these are obtainable. Here's the second one. You're allowed a calculator. This looks like an area volume type problem. Let R be the region enclosed by the graphs of f of x and the horizontal line y equals 4. As shown in the figure above, find the volume of the solid generated when R is rotated about the horizontal line y equals -2. It might be a bit lower than this on my graph, but I know it's somewhere below this region R. And so when I rotate this about this line, perpendicular to my axis of rotation, I'm going to have very thin dx values. I just need to figure out how big the radius of these washers is going to be. Again, I have this section here where nothing is there to rotate, and so I'm going to have washers. Big R, when in doubt, you can write it as top minus bottom, the top being 4, the bottom being -2. And if you see here at the bottom, that comes out to a big radius of 6. My little radius is again top minus bottom, the top being f of x, the bottom being -2. And when I do f of x minus a -2, it's going to be f of x plus 2. Now, I do have access to a calculator, so what I can do is write out my integral as pi times the integral from 0 to 2.3. We'll talk about where this value comes from. Big R squared, which is going to be, 6 squared, minus little r squared, which is y1, if I typed that in as y1, plus 2 quantity squared. Let's go back and talk about this upper limit of integration. The picture didn't tell me that this was at 2.3, but what you can do is graph y1 and graph the line y equals 4. Second Calc 5 will help you find the intersection of any two lines. It will tell you 2.3. So from 0 to 2.3 is the section I'm revolving about the line. And if you're careful typing this in, you should get about 98.868 for the volume. 2 points for the integrand, 1 point for your limits, and 1 point for your answer. This one's only 3 parts. On to B. Region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. This part makes it actually really easy. Find the volume of the solid. When in doubt, the volume, if your base is, if there's going to be a shape kind of branching from this base, my shape being isosceles right triangles, the volume is going to be the integral of the area of these right triangles. And so if one leg is here, it might come, branching off the top here, and I'd have this right triangle. The base and height are going to be the same. And so notice my base is just top minus bottom. So here's the area of any triangle, 1/2 base times height. The base being top minus bottom here, matching the height means that I can just set h equal to b, and I could make this represent my area. And I'm just going to put top minus bottom in for b. What's nice is I think we did a top minus bottom earlier, so I just pulled that, I think it was 4 minus f of x. No, I did top minus bottom slightly differently. For region R, it's going to be 4 minus f of x. And if I have that stored as y1 in my calculator, I can type this expression in. I should get 3.574. 2 points for the integrand, 1 point for your answer. For the next one, they're looking for a specific k value that breaks this region R into 2 sections of equal area. Write but do not solve an equation involving integral expressions whose solution gives the value k. So there's some sort of k value that might break this up into 2 sections of equal area. I just want the area from 0 to k to match the area from k to 2.3 because it's going to be cutting it into equal areas. My top minus bottom is 4 minus x for R, and we're done. I don't have to solve for what this k value is, but if the area under the curve from 0 to k matches k to 2.3, then this is a way I could set this up and solve for k. But they don't ask us to do that. Area of one region and equation are both a point for 2 total. This is the rest of the calculator section for 2014. The rest of this we have to do the old-fashioned way, by obsessively color coding everything. So visualizing this, maybe illustrating it would help you if you have access to this. We have the graph of f And I'm told that g represents the area under the curve of this f function from -3 to some value x. You'll see this a lot through AP Calc AB. If I'm asked to find g of 3, I'm just going to plug a 3 in anywhere there's an x. And so g of 3 is going to be the area under the curve from -3 to 3 of f of t dt. I would recommend breaking this up into a whole bunch of different areas. It's a whole bunch of triangles, and I think I have a trapezoid here at the end that I decided to split this up. I think you'll see why a bit later. From -3, I have the orange and the green, and then to 3, I get to the blue. This is why I broke that off initially. It's below the x-axis, so that integral will give me a -1. So make sure you're aware below the x-axis, it's not a negative area, but the integral gives you a negative value. Combining orange and green, I get 10. Take away 1, you get 9. For 1 point. On what open intervals contained from -5 to 4 is the graph of g both increasing and concave down? If I want to know when g is increasing, I want to know when its first derivative is positive. And when it's concave down, I want to know when the second derivative is negative. So let's find when the first derivative is positive. I first want to find g prime of x. Well, if g of x equals the antiderivative of f of t from -3 to x, when you take the derivative of this with respect to x, the derivative of g is g prime, and the derivative of this integral is just f of x. Notice the x replaces the t's. And so I want to know when g prime of x is positive. This is when f of x is positive, and that happens really all of this section. We have f giving positive values. Notice not at -3, but that might not be too important. But specifically, -5 to 2 is a section where it's at or above the x-axis. And notice with parentheses, I exclude -3 here. Concave down is when my second derivative is negative. My second derivative would be the first derivative of f, and this is just asking when the slope of f is negative. When f is decreasing, that happens from -5 to -3, from 0 to 4. I really just need the overlap of these intervals. One of them was, for the most part, everything in between here. The other one was this section and this section, and there are going to be 2 intervals that overlap. -5 to -3 is one of those they have in common. These don't fully overlap, but they do overlap from 0 to 2. You can write these as intervals, open intervals, or with inequalities. They're looking for a reasoning here for how you know this is both increasing and concave down. I know it's increasing because g prime of x is positive, and I know it's concave down because g double prime of x is negative on these intervals. 1 point for your answer, the intervals, and 1 point for your reasoning. C, the function h is defined by this rational function, g of x on top, 5x on bottom. Find h prime of 3. I'm just going to rewrite this and then take the derivative of both sides. Therefore, h prime of x is going to equal a quotient rule. So a prime b minus ab prime over b squared. I write out my quotient rule. If I want h prime of 3, I plug 3's in where they go. G prime of 3 is going to give me f of 3, and I can get a -2 value there. This is 5 times 3, which is 15. G of 3 is actually something we found in part A. It comes out to 9. 5 is 5. If I plug a 3 in the denominator, I get 15 times 15. You can do napkin math to the side to get 225, or maybe you leave this as 15 times 15, because eventually I'm going to have to simplify a little bit. Just know that even if you get to a step like this, you don't have to simplify this. If it is equivalent, you can write this and you're done. But if you simplify it improperly, you are likely not going to get the point for your answer. But leaving it unsimplified is sufficient. Notice it's 2 points for taking the derivative for running this quotient rule. So quite a lot here if you are good with running that quotient rule. The function p is defined by f of x squared minus x. Find the slope of the line tangent to the graph of p at the point where x is -1. I'm just going to start by writing this and thinking about what it means to find the slope of this. So if p of x is this, if I want to find the slope, let's find p prime. If I take the derivative of the right side, the derivative of f of something is f prime of something, and the chain rule comes in. Notice that 2x minus 1 is the derivative of x squared minus x. I just want the slope at a specific coordinate. I want the slope at -1. You plug -1 in where they go, and if you're careful simplifying, you should get 6. 2 points for applying this chain rule properly, and a lone point for simplifying to get your answer. Number 4, these are known as a tabular type of problem. Anytime you have a table and maybe have to do average rate of change or a Riemann sum. This table represents the time and velocity of a train. I believe train A heads a certain direction, east and west, and later on we're introduced to train B, which goes north and south. Let's start with train A. Train A runs back and forth on an east-west section of a railroad track. Train A's velocity, measured in meters per minute, is given by a differentiable function, v of t, subscript a, va of t, where t is measured in minutes. Selected values for va of t are given in the table above. Find the average acceleration of train A from 2 to 8. So I'm really just looking here from 2 to 8. The average acceleration, I like to write this out and think what they're looking for here. Average rate of change is a formula I'm pretty good with using, and the rate of change of velocity is acceleration. So you can think of this as the average acceleration. It is going to be, again, my average rate of change formula for my velocity. Va of 8 minus Va of 2 over 8 minus 2. So a 6-minute interval where my velocity changes from -120 to -100 for -110 over 3 minutes, miles per minute per minute. Let me double check my units here. Meters per minute. I guess MI would be miles. Meters per minute. Because it's acceleration, it's a rate of a rate. 1 point for that average acceleration. B. Do the data in the table support the conclusion that train A's velocity is -100 meters per minute at some time t, with t being between 5 and 8? Give a reasoning for your answer. So I'm just looking between 5 and 8 and wondering if the velocity is ever going to be -100 here. Thinking about this, we go a velocity of 40 and it gets to -120. You want to ask the question, is -100 within this range? I would say, of course. Now, this function might have a jump or some sort of discontinuity. It might not be differentiable. There's a lot of things that can happen between 5 and 8. But here, highlighted in pink, they tell me it's a differentiable function for velocity, which tells me that it's continuous. And if it's continuous, I'm going to hit absolutely every single velocity between these from 5 to 8 as it changes direction in a way. So here's what I say for this one. The velocity of A is differentiable, therefore it's continuous. And if it's continuous, I'm going to hit every single thing between V of 5 and V of 8. The intermediate values theorem, IVT is going to apply here, IVT. So I like to state these. I'm not sure exactly if you need to write them out yourself, but this is exactly what I was saying earlier. We have a velocity of 40. It changes to -120. IVT guarantees that it'll be -100 somewhere because -100 is in the middle of those two values. It's inside that interval. By stating that -100 is between 40 and -120 is a point. Stating that you know the intermediate value theorem guarantees this is another. They are also fine with you using the acronym IVT, so keep that in mind. At time t equals 2, train A's position is 300 meters east of the origin station, and the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time t equals 12. I'm really thinking fundamental theorem of calculus here. And for FTC, there just needs to be 2 times that you either know or care about. And so there's actually a lot they tell me here. They tell me what's happening at time 2, and I want to know what's happening at time 12. So if I set up the integral, 2 to 12 of v of t, I can just state that 2 to 12 will be v, or my position of 12, minus my position of 2. Or you can jump to your rewriting of the fundamental theorem of calculus here, where I'm solving for my position at 12. It's going to be where I started at 2, and then the distance traveled from there. They tell me, I think, 1 or 2 of these values. The location at 2 is 300. And then this is what we call the area under the curve of velocity, and they said specifically to use trapezoidal sums to approximate this. This is from 2 to 12. 3 trapezoids, so one of them is going to be from 2 to 5, one of them from 5 to 8, one of them from 8 to 12. You're going to add these values together, divide by 2, and multiply by the width of these trapezoids, so by 3 for that one. 100 plus 40 divided by 2, and it's a change in x of 3. The next 2 values, 40 and negative 120, divided by 2 times 3. The next 2 velocities divided by 2 times 4. Notice it's not a consistent width for all of them, so you can't just pull a 3 out from all of these. Good luck simplifying these. I think this is one where I got 140, cut it in half to get 70, times 3 was 210, no problem. 40 plus negative 120 is going to get me negative 80, divided by 2 is negative 40, times 3 is negative 120, no problem. You could run into issues depending on how you simplify this. In fact, I probably could have canceled these and just multiplied this by 2, but I did a little bit of napkin math over here to do that. That could show up for negative 540. It simplifies to negative 450. Therefore, my position at 12 is equal to where I started, plus some change in distance for negative 150. It means that over this time I've moved left quite a bit, because I started quite a bit right at 2. The position of train A at time t equals 12 is approximately 150 meters west of origin station. Position expression, trapezoidal sum, and position at 12 for a point each. This last part is probably the hardest of all the free response from this year. It is where we have to work with related rates. We bring in train B, which moves north and south, and they give me a velocity model for B. At time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at a specific time. I think the best way to go about a problem like this is to visualize it. So I made a note. Here's a new equation I might want to use, the velocity of B. Here is the origin, or origin station. And at t equals 2, train A is 300 meters east. Train B is 400 meters north. And I could find their current distance from each other, but as time moves on from this, from t equals 2, they might be heading different directions, and this distance very well could change. And that's what they're looking for. What is the rate that the distance is changing? Right away here, there's a 3, 4, 5. That might come into play in just a bit. But I know that whatever this x distance is and this y distance, the Pythagorean theorem is going to work here, and this is what I wrote out. The x location of train A and the y location of train B is going to equal their distance squared. If you differentiate this with respect to time, I get 2x, chain rule implies dx dt, 2y, another chain rule, dy dt, 2z, another chain rule, dz dt. And thankfully, from the prompt, they give us a whole lot of this information. From part C, train A at this time is 300. Did they say meters or miles? Meters east of the origin station. Y is 400 meters north. And from the Pythagorean theorem, I can use a 3, 4, 5 Pythagorean triple to get Z to be 500. That's the distance at that time. Some of these other values, the change in x per change in time, at 2 is 100. I get that from the table above. So I'll plug 100 in for dx dt. dy dt, they gave me the velocity for b, so I can plug in 2 there. And the math to simplify that one was not too bad to get 125. From here, I just want to solve for dz dt. I would recommend, and you don't have to do this, but if you notice everything is divisible by 2 and everything is divisible by 100, you can just divide both sides of the equation by 2 and by 100, and it gets you a 300 here, a 500 here, and this just simplifies to 5. Very nicely. This is a lot easier for me to work with. Again, you can write your fraction as 800 divided by 5, or if you know to simplify that, you can. Keep in mind, I don't have a calculator for this, and if I mess this last step up, I could lose a point. 2 points for your implicit differentiation of a distance relationship, really taking the derivative of this properly, and then 1 point for simplifying to something equivalent to our answer. That's free response question 4 down. There's 2 more to look at. Here we have another table that really helps me kind of think about 2 different functions, f and g. The twice differentiable functions f and g are defined for all real numbers x. Values of those functions and their derivatives are shown in the table above. Find the x-coordinate of each relative minimum of f from -2 to 3. Justify your answer. So if I'm looking for a relative minimum, I'm looking for when the first derivative is 0 and changes signs, specifically from decreasing to increasing. Find when f prime of x equals 0 and changes signs. Looking at the table, x equals 1 is the only critical point at which f prime changes signs from negative to positive. Therefore, it's our minimum. Let's look at what happens at x equals 1. My slope is 0, and it went from decreasing to increasing, from negative to positive. This is where your minimums occur. As opposed to this other time when your slope is 0, when it goes from negative to negative, this is not a relative minimum. So x equals 1 is the value. Explain why there must be a value c between -1 and 1, such that the second derivative of c is 0. So I want to look at -1 to 1. I'm working with the f function here. I know that f prime goes from 0 to negative to 0. And so there are 2 things I can think about here to prove this. Using the mean value theorem, and to use this, first thing I want to do is state that f and f prime are differentiable. Therefore, mean value theorem is going to apply. It specifically needs to be continuous, or you can just say it's differentiable, which implies continuity. If I run the average rate of change of f, this is going to tell me the average second derivative from 1 to -1, and it ends up being 0. And I know that it by the MVT, there's going to be a c value that matches this average rate of change. So mean value theorem is a great way to get there. If running this average rate of change was a bit tricky to figure out yourself, here's a graph of potentially what f prime of x looks like, where I said it was 0, and then f prime goes to negative, and then f prime goes to 0. F double prime would describe the slopes of this, and I hope you can agree, if it goes from 0 to negative values to 0, there's going to be a relative minimum within that interval. Stating that the difference in slopes is 0, and using the mean value theorem are a point each. The function h is defined by h of x equals the natural log of f of x. Find h prime of 3. Show the computations that led to your answer. I always like to write the equation they told me for h and then say, well, let's take the derivative of both sides. The derivative of h is h prime of x. The derivative of the natural log of something is 1 over something. And then chain rule states I take the derivative of the inside. And if I plug a 3 in everywhere they go, I think the table has both of these values, and you just simplify and you're good. D is the last one, and it's a bit tricky, and you have to think outside the box a little bit. Evaluate this monstrosity. Okay, let's just write this and stare at it for a bit. The antiderivative from -2 to 3 of f prime of g of x times g prime of x dx. This looks so familiar. In fact, with g being on the inside and its derivative being on the outside, it looks like some sort of chain rule happened to get this. So my question is, well, let's think how this came about. If you take the derivative of f of g of x, the derivative of f of something is f prime of something, and the chain rule brings a g prime of x out. So I'm looking for the antiderivative of this, evaluated at 3 and -2. Therefore, if the derivative of something is this, the antiderivative means that I can go backwards. F of g of x must be the antiderivative of this expression, and I can verify that this does give me that as a derivative. I plug in 3 and I plug in -2, and if you're careful, the table has all of these values, and you simplify. It's a lot of thought that goes into a problem that they think is worth 3 points. 2 for using the fundamental theorem of calculus, and 1 for your answer. One problem left to look at. A differential equations question. These, for sure, show up on a lot of AP Calc free response sections. Consider the differential equation dy dx equals 3 minus y cosine of x. Let y equal f of x be the particular solution to the differential equation with initial condition f of 0 equals 1. I highlight this and circle it and star it, and I know I need to use this at some point for a point later on. The function is defined for all real numbers. A portion of the slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. Definitely start at 0, 1, and do not be like those students that put it here. Notice that the way your axes are labeled is that if this is 3, this is 2, and this is 1, and your y-axis follows suit. So 0, 1 would be here. Make sure that your slopes at specific times are pretty close to the slope field, and you should be okay. I'd say that you all can absolutely nail this one for the 1 point. Part B, write an equation for the line tangent to the solution curve in part A at the point 0, 1. I don't know exactly what it looks like, but I do know at 0, 1, it's got a steepness of about this. So I'm going to try and create that tangent line that goes through 0, 1. If I'm creating a line, you bet I'm going to bring out either point slope form or slope intercept form. I just need to find the steepness. So I have an equation there, dy dx, to find the slope at any coordinate. What is the slope when x is 0 and y is 1? So I input 0 for x and 1 for y, and you just simplify. Keep in mind cosine of 0 all the way on the right side of your unit circle is an x-coordinate of 1. 2 times 1 is 2. So I have a slope. I just need to plug in my coordinate of 0, 1 and rewrite this. Again, slope-intercept form would also be sufficient here. This is my line of x, or y, which is 2x plus 1. They said to approximate what happens just a bit to the right of 0 at 0.2. So here's what I declare. My approximation for f of 0.2 is going to be pretty close to what this line is doing at 0.2. And if I plug in 0.2 here, it simplifies to 1.4. Creating the tangent line and using the tangent line are a point each. Last part. Find the equation y equals f of x, the particular solution to the differential equation with initial condition f of 0 is 1. I believe on this year's mock exam, we had one of these where this was worth about 5 points. Back in 2014, they made it worth 6. Having this in your pocket, being confident about separating and integrating, is worth a whole lot of points. So make sure we lock in here. I'd start by writing out the differential equation. Separate your variables. X terms on one side, y terms on another. I'm going to divide this to the left side and multiply the dx over. Just by separating, you get a point, and you have to separate to get any points below. So make sure you remember to separate. Then I integrate both sides. Right side, I'm pretty good. The antiderivative of cosine is sine. I'm not going to forget my plus c. On this side, the antiderivative of 1 over y is natural log of the absolute value of y. If this is anything else, you might want to use u substitution to see exactly what it comes out to be, but here's the shortcut. As long as there's no funky exponents on y here, this is going to be inside my absolute value bars. If your variable is positive, you do not need a negative out front. Because this one is negative, if you do run u substitution, you'll see very clearly why a negative shows up in front. So if I have 3 minus y, negative in front. If it's y minus 3, I don't need a negative in front. Keep in mind that those antiderivatives are a point each, and this year, writing your constant of integration plus c is a point. I know you will remember that and get that point. I'm going to plug in my coordinates 0 and 1 for y and x and solve for c, and you get c to be the negative natural log of 2. I can then rewrite my solution with the negative natural log of 2 and just solve for y. I'd recommend not having a negative in front like we have here. I'm going to multiply both sides by negative 1 to deal with that, and then raise both sides to be an exponent of e. On the right side here, you can break this up into e to the negative sine of x and e to the natural log of 2. And using your rules of logarithms, e to the natural log of 2 is just 2. I can subtract 3 from both sides and multiply by negative 1, and we get our particular solution. The steps here at the end could be a bit confusing, but it's something we've done a lot in class, and I'm pretty confident that you will remember the steps here. Separate's a point. Both antiderivatives are a point each. Adding c is a point, using your initial condition of 0, 1 as a point, and writing your particular solution at the end as y is a final point. This is the free response for 2014. If we look back at the common sections, we definitely had, as we just did there, a differential equations problem. Particle motion is very, very similar to that train problem we had, where I have left and right or up and down motion described by velocity. We had 2 problems with tables, one of which could be interpreting a graph if you did do a little visualization yourself. We definitely had one that was the area under the curve that could be interpreting a graph there. We definitely had an area volume type free response question. If you have any questions, do let me know, and best of luck on your AP Calc exam.